The next speaker is Mark Mockren. He's the VP of Product Architecture at Pliops. He has extensive storage systems experience, having held leadership positions in engineering and marketing at Marvell, EMC, Broadcom, and Lightbits Labs. He co-founded Cepiton, previously Sungate Systems, which was acquired by Hitachi Data Systems. Mark's BSEE is from University of Pennsylvania, and his MSEE and MBA degrees are from Israel Institute of Technology.
Hi, I'm Mark, and we're from Pliops. So the company is based in Tel Aviv. We have an office here in San Jose, 40 employees right now. First product will be released towards the end of the year. And you can see the list of investors down at the bottom. Some of them are here and are hosting us indeed, Western Digital and Xilinx. And you can visit us at their booths at the expo. What's happening really in data centers over the past few years? What's happening is that the performance of storage over the past few years has gone up by over 3 orders of magnitude, right? About 5 years ago, most databases were stored on hard drives and with about 100 IOPS per drive. And right now, with NVMe SSDs, each drive easily supports over 500,000 IOPS. So over 3 orders of magnitude increase. Networking has increased from 1 in 10 gigabit per second to 100 gigabit being mainstream today, and people moving towards 400 gigabit in the not far away future. But on the other hand, the CPUs are kind of stagnating, with performance growing at a rate of about 3% a year, doubling at a rate of once every 20 years at the current existing rate. So with the tremendous growth in performance of storage and of networking, essentially what's happening is that customers are limiting the capacity per box and building lots and lots and lots of boxes, causing really a huge sprawl in the data centers and increasing costs quite a bit. And so what are people doing with these NVMe SSDs? Well, mostly storing databases on it, with databases growing in the near future, cloud databases being a $20 billion business, and also the analytics business as well, growing toward $40 billion business as well in the next couple of years. So all this data stored in all these SSDs, the databases today have a lower layer called a storage engine, which is responsible for storing the data and retrieving the data from the storage. The storage engine typically keeps the data sorted, right, for the databases and for the analytics engines. Usually storage engines, traditionally, they're based on B trees, and we'll talk about that soon. And recently, a new design called LSM, Log Structured Merge Tree, has become very popular, with RocksDB being the leading implementation. And these storage engines they're very complex, and they're prone to variable performance. Why are these storage engines inefficient and prone to variable performance? Well, essentially, what they need to do is they need to map variable size data into fixed size blocks. So how to do that? That's actually quite a difficult problem. And there are various trade-offs which they all need to make. One, for example, can keep a huge memory map to map this variable size data to the fixed size blocks. Or in some implementations, there is less DRAM being used at the cost of multiple accesses to the flash to fetch the data. There are various trade-offs of speed versus space efficiency. There are very high CPU and I/O costs for sorting the data and resorting the data and garbage collecting the data. And as was mentioned in previous lectures, there is a very high read and write amplification in these implementations. It could be from 20x to over 100x, depending on the architecture, depending on the key value size, and so forth. And when we're dealing with such high write amplification, we're reducing the flash lifetime, or alternatively, we're buying more expensive flash than we maybe need to. And we're also reducing the application bandwidth, right? Because we're using a lot of bandwidth to garbage collect and resort the data. And additionally, when you think about it, when you're talking about write and read amp of 20x, 100x, so if you have, for example, an incoming write bandwidth of of 100 megabyte per second going into a server, which is not a lot, that translates on the back end to the drives of traffic in the multi-gigabyte per second range. Okay, so if you're talking about disaggregated storage, this is all traffic that goes on the network. And therefore, the networking companies are extremely satisfied. This is what's driving some of the 100 gigabit and above networks, which are extremely expensive. So this is all these issues are indeed very, very problematic, and they end up costing the customers a lot of money. So what are we doing at Pliops? We're looking at the storage engine, and we're replacing it with a hardware-based storage engine. On top of that, thin driver layer, with most of the heavy lifting, the I/O intensive, the CPU intensive work being done by the hardware. So what does the hardware do? It essentially, first of all, it manages in highly compressed format the object memory map. This is extremely memory efficient, and it's a compressed format, which really, in order to get good performance out of it, you really need the hardware to manage that. With the software alternatives being much more expensive, typical software-based key-value systems often operate at something about 10 to 12 bytes per object. We're doing this at much less. The hardware takes care of things such as key sorting, garbage collection, compression, encryption, and of course dealing with all the issues around data persistency, power fail, and so forth, logging. And with the whole point of the hardware freeing memory and compute resources to run applications and not manage storage. Now, if all this stuff that we're doing is offloaded by the hardware, there's a lot less CPU consumption, and therefore we can really put a lot more flash into the servers, with the point being to reduce, of course, the server sprawl that we mentioned earlier. This is just a comparison of POC board being compared with RocksDB. So this is a benchmark of reading while writing, and we're seeing with the Pliops-based device 13x improvement in performance. This is on top of a single 1 terabyte NVMe SSD. And if we're normalizing this to per CPU core performance, the improvement is 62 times the performance, and the tail latency is 3 orders of magnitude less. This is the 4 nines tail latency with the Pliops device. So this is dbbench, which is really an artificial benchmark. So now let's see a real life use case. And for this, we'll take a look at MySQL. So MySQL uses, for its storage engine, uses InnoDB, which is a B-tree-based storage engine. I don't know how many of you guys know much about B-trees, but B-trees of course, are tree-based structures consisting of blocks with a fixed maximum size, and with InnoDB, the default is 16K bytes. So the data key values are stored in the leaf nodes, and the root node and the inner nodes, essentially, they point your way towards the leaf that will contain the key value that the database is looking for. Once the block grows beyond its maximum size, it needs to be split to 2 blocks, and if the inner node above it needs to be updated as well. And of course, similarly, blocks can also be merged when it gets below minimum size. InnoDB and most B-tree implementations are write-in-place architectures, which means that if we have a file that contains the B-tree nodes, if we're deleting nodes inside the B-tree, we're not really reclaiming disk space. The file still is the same size. And importantly, the space used per block is the block size. InnoDB will always allocate 16K bytes or 8K bytes, whatever you configure the block size, to be the physical block size, no matter how many KVs are actually written into that block. So if we're looking at the space advantage on MySQL, this is just to give you an example. So on top, we can see it could be a typical 16K byte block in InnoDB. So there would be about 11K bytes, let's say, of data, with about 5K bytes of empty, wasted space. If you can, in MySQL, turn on compression, what that will do is you need to you have an uncompressed block size, in this case 16K bytes, and you tell InnoDB what is going to be your compressed block size. So usually people will say, for example, 8K bytes. So with 8K bytes, that's still a fixed block size. So data, let's say, will be compressed to maybe half of what it was in 16K bytes. And again, we still have the wasted space inside the block. If the compression ratio is less than 2, and we're not really being able to compress for overflowing the 8K block, then we get into more issues, into more performance issues. So this is again an example of how difficult it is to manage variable size data on top of fixed size blocks in software. So at the bottom of the diagram, what you can see is what it looks like with Pliops. We would take that block, we fully compress it, we store the blocks sequentially on the drive with 0 gaps between the blocks, essentially with full space efficiency. And so on top of, let's say, InnoDB uncompressed, we're saving about 70% space and saving about 33%, 34% on top of InnoDB compressed. And we can see here an example. This is a real-life example. This is Percona is a company that builds management for databases, and using their monitoring PMM, their monitoring management tool, we can compare the MySQL versus Pliops-enabled MySQL and see the performance and efficiency benefits. So we're saving 70% of space on top of uncompressed MySQL, doing 3x faster queries per second because we're writing a lot less, we're reading a lot less. Additionally, one thing that we need to mention in InnoDB, and this is also, again, a problem that we see with a lot of databases, there is a problem of atomicity when writing to a block device. So for example, if you're writing a 16K block to storage and there's a power fail in the middle, you could corrupt that 16K block, right? Because a disk, a typical SSD will write with an atomicity of a single LBA, which is 4K bytes. So how does InnoDB solve this problem? It has this mechanism called a double write. So essentially, before it updates the B tree, it writes the exact same block to somewhere else called the double write buffer. And then if there's a power fail, it scans essentially a double write buffer and the blocks in the B tree to see if any of them are corrupted. So essentially, InnoDB will write every single block twice. So, but since we're dealing at the key value level and our key value operations are atomic in nature, then we're also avoiding this double write scenario. So at the end of the day, as far as performance, we're seeing half the amount of reads from storage, and we're actually writing 1/7 the amount that InnoDB is writing for the same benchmark, same database. So this is all actually working, and you can see this. Come visit us at the WD booth and the Xilinx booth on the floor. The next steps, we have this MySQL POC demo working, and we're eager for other people to try it out, and would like to get feedback from you guys. We'll be having solutions for other databases coming up soon, including for Redis. We're also going to be doing a compressed block device, essentially with the same technology, being able to manage compressed SSDs in the same fashion. If you compress an LBA, of course, that becomes just like any other key value, and so we handle that efficiently. So we'll be offering that kind of product as well. And next year we'll be offering optimized storage engine solutions that could be integrated into third-party applications.
You mentioned that you have different solutions for different databases. Is it that there's no common key value interface that would be sufficient?
So essentially, if that's correct. So in each database today implements its own storage engine, and they all have their own APIs. In MySQL, it's InnoDB, and with MyRocks, it's RocksDB.
But couldn't there be some common underlying abstraction, and then the rest is on the host side?
There are common similar APIs. They all have, of course, put, get, delete. There are iterators, snapshots, but the actual implementations are different. And there are some storage engines that have additional APIs, which other storage engines don't. So there are common themes, but there is no standard in this space.
So your storage engine, is it sitting in a box with the flash storage, or is it sitting with the host? And how do you communicate between the storage engine and your actual storage?
Okay.
What protocol are you using?
We have a POC today, which is a Xilinx development board with an onboard open channel device, or actually a standard block device as well. We're doing both on board. So in this case, we're talking NVMe to the drive. We're the host to the drive, and we have our own driver which we supply to the host software. So that's one model. But we're also working on an accelerator type model as well, where the host will talk with our controller, and the host will then, based on inputs it gets from our controller, then we'll issue the IOs to the SSDs. So we can do both. We can have the SSDs controlled by host software, or by our hardware. Okay.
So after you compress, the data size could be changed, right? So how do you manage this different size of the?
So this is really part of our core IP, is being able to very efficiently manage this variable sized memory map. That's the secret sauce. Yeah.
Yeah. So do you have your own controller chip or anything?
Yeah. So we're developing. I mean, right now, the POC is an FPGA, and we're looking towards ASIC in the future as well. Yeah.
What about using the standard or upcoming standard for key value command set?
We're looking at that as well. We're on top of that. So as that standard evolves to meet our needs and to meet our customers' needs, then we'll be using that. But today, it's not something that we're seeing. For example, databases implementing that kind of API. So
if you find that the current proposal is deficient in some ways, would you sort of bring it up so the
of course,
standard can?
yeah, we're part of the working group, and we're interacting that. We're there.
There's time for one more question.
So in your second model of operation, when you have one accelerator and talking to multiple standard NVMe SSDs, is the host talking to your controller first?
So as the accelerator, yes. So it would be.
So basically, that's a master. Your controller is a master.
It could be, but it doesn't have to be. In the existing POC, it is the initiator towards the NVMe SSDs. That's what we have implemented today. Okay, but what we're working on as well is an accelerator model where the host CPU speaks with our controller, and then, for example, we'll ask the controller, where is this key value residing? The controller will stores the location. We'll give the response to the CPU, and then the CPU can issue a read request to the location on the SSD.
So today your POC is a kind of assistant.
Right. Today in the POC, the host does not see the drive. But in the future, the host will see both the drive and the SSDs. So potentially, for example, the SSDs could also be over the network as well. The software will just issue a read-write to a block device.
Thank you.
Okay.
So your controller is using a custom driver.
Correct. Yeah.
And the controller is managing multiple drives. Is that the idea?
Yeah. Okay. Thanks, guys.